Let's take a look at how we do adding, subtracting, multiplying, dividing of complex numbers, and see how different forms of the complex number lends themselves to easier algebraic or arithmetic computations. We have two different complex numbers here, z1, which is equal to 4 plus j3 in rectangular coordinates. In its polar form, z1 is also equal to 5 angle 37.87 degrees. And of course, in its complex exponential form, which is, or still polar, still has the polar values, magnitude 5, angle e to the j, angle 37.87 degrees. And z2 equal to 2 minus j5. In polar form, it's that. In its complex exponential form, it's that. And let's just plot these out, kind of right here, tuck it in, just so that we can see what we have here. In the complex plane, we're going over 4 and up 3, so it's about like that. And on this one, we're coming over 2 and going down 5, so maybe it's down here something like that for z2, and that's z1. All right, let's start this off by just adding z1 plus z2. z1 plus z2. Addition is most easily done in rectangular coordinates because in that you simply add the real parts and the imaginary parts. So z1 plus z2 would be 4 plus j3 plus z2, which is 2 minus j5. And when you do that, you get, let's see, 4 plus 2 is 6, and j3 minus j5 is a minus j2. Pretty easy. Alrighty, how about multiplying? Let's do z1 times z2. Well, before we go on, let me just say that multiplying in polar, or adding in polar form really isn't very, polar form isn't conducive to adding unless you want to do it graphically. And of course, adding graphically, you take z1 and z2 and you tip to tail them. So if that's z2, then you'd add in z1 like that, and the resultant vector, or the resultant complex number, would be that. Generally speaking, we don't add in polar forms unless you're using your calculator, and your calculator can do all things. So now, let's look at multiplying z1 times z2. We get then, z1 is 4 plus j3 times z2, which is 2 minus j5. And we see here that we have two binomials multiplied together. That means we need to FOIL them, distribute both of these terms to both of those terms. And when you do that, you get 4 times 2 is 8. 4 times a minus j5 is a minus j20. j3 times 2 is a plus j6. And j3 times minus j5, we've got to be careful here. 3 times 5 is 15, but we've got to be careful with the sign. Plus times a minus is minus, but j times j is a negative 1. So we have a minus times a minus, that becomes plus. So we have two imaginary terms, two real terms. 8 plus 15 is 23. And the negative j20 plus j6 is a minus j14. So, multiplying two complex numbers in rectangular form requires us to FOIL them. I'll leave it to you, and you stop the video right here and go ahead and convert this rectangular complex number into its polar form. Let me just give the answer. The answer is 26.93 angle negative 31.33. Alrighty. Now, let's multiply z1 times z2, only doing it in polar coordinates, using our polar form of these. In polar, we have z1 times z2, that's equal to 5. I'm going to write it using its complex exponential form. 5 e to the j 37.87 times z2, which is 5.39 angle negative, oh no, whoops, I'm doing an exponential form, e to the negative j 68.2. Of course, these two forms are equivalent forms. It's just that it's more obvious what we're doing when we write them as exponentials. So when you do that, 5 times 5.39 is equal to 26.93. Now we have e to the j positive 37.87, and we have e to the minus j 68.2. So when we add the exponents, the negative 68.2 plus the j 37.87 gives us an angle of, so it'll be minus j angle 31.33. And what we see is we get the same answer foiling and then converting to polar as we did by just starting out in polar form and multiplying the coefficients and adding the exponents. I'm going to leave it to you to take and convert this expression here in polar back to rectangular and convince yourself that you get the same thing there. Go ahead and stop the video and do that now. Alrighty. Now we've got addition. By the way, I should have mentioned that subtraction is just the same as addition, only you're subtracting the real parts and subtracting the imaginary parts. We've now done multiplication in both rectangular form and in polar form. Now let's look at dividing two complex numbers. Let's do z1 divided by z2. You'll recall from your from your college algebra that this gets to be a little bit ugly, well, at least a little involved. We've got 1 in doing this in rectangular form. We have 4 plus j3 divided by 2 minus j5. You'll recall that in college algebra they taught us to do this division by multiplying numerator and denominator by the complex conjugate of the denominator, effectively rationalizing the denominator so that we get a pure real number in the denominator, and then the numerator falls wherever it may. So we're going to multiply numerator and denominator by 2 plus j5 over 2 plus j5. 2 plus j5 is the conjugate of 2 minus j5. Now you can go through and do the foiling because we have this complex number times this complex number. It's got to be foiled. I'm going to leave that to you to show that it turns out to be negative 7 plus j26 divided by, now let me show the details down here just to remind you what happens here. We've got 2 times 2 is 4. We have 2 times a positive j5, that's a positive j10. Now we have a negative j5 times 2, that gives me a minus, that's a j10 there, minus j10. And then we have the negative j5 times a positive j5. We've got to be careful with the signs here. 5 times 5 is 25. J times j is a negative 1. Minus times a plus is a minus, so we've got a minus from the signs, a minus from the j squared. That gives us a positive. So this then turns out to be negative 7 plus j26 divided by 29, which works out to be equal to negative 0.24 plus j.9. So the division of z1 divided by z2 in rectangular coordinates gives us this rectangular coordinate. Now, oh goodness, let's go ahead and convert this to polar coordinates. In polar coordinates, we're going to have the magnitude of that is equal to the square root of negative 0.24 squared plus 0.9 squared. That turns out to be 0.928. That's the magnitude. Now the angle. The angle here gets to be a little bit tricky. The angle is going to be the arc tangent of 0.9 divided by negative 0.24. Okay. Now, the arctangent button on your calculator returns a value between plus or minus pi halves, or plus or minus 90 degrees. This becomes ambiguous. To find out what the actual angle is, you take the arctangent of 0.9 divided by negative 0.24, and you come up with a negative 75 degrees. So this turns out to be 0.928 angle negative 75 degrees. But that's not exactly right. Coming back here and looking at our complex number, we see that we are in not the fourth quadrant. Negative 75, I'm running out of room. Let's just draw this down here. It has us down here at negative 75 degrees. But when we look at this number here, we're at negative 0.24. The real part is negative, so we're over here and up 0.9. In reality, where we're at with this complex number is 180 degrees off from this negative 75 degrees. And so the actual angle is negative 75 plus 180. This angle right here is actually 105 degrees. So when you're doing it in rectangular coordinates using your arctangent button on your calculator, you've got to be careful and look at the actual coordinates that you're working with, because your arctangent button can cause you some grief. Let's do this calculation directly from polar form, and we have then z1 over z2 is equal to, in polar form, z1 is 5e to the j 37.87 divided by z2, which is 5.39 e to the minus j 68.2. Now we can do that directly. And 5 divided by 5.39, that is in fact equal to 0.928 e to the, now the exponent is going to be j, and we've got 37.87 minus 68.82. That turns out to be the 105. There's some round off error there, but it's a positive j 105 degrees. When you do it this way, already in the polar form, the ambiguity that the arctangent button introduces is we avoid that ambiguity.